Okay, so Zoom is recording. All right, so let's get started. Okay, so last lecture we talked about how phase transitions happen, and we discovered that it happens because of ergodicity breaking. I didn't prove it to you, I just told it to you. And the idea was basically that what you can see on the left-hand panel, namely that when I'm above the critical temperature, the system is ergodic over all of its phase space. And ergodicity means that we can replace the time average of a quantity with an average over a probability distribution. And the probability distribution that gives you the right answer is the Boltzmann distribution, or the Gibbs distribution more generally. And that's the foundations of statistical mechanics. Now, that in the picture on the left, you can see over here that the trajectory samples all of phase space, and because it samples all of phase space, it counts as many states up as are pointing down, and so the net magnetization is 0. So when we say that we have a phase transition below Tc, the only way that can happen is if the system breaks ergodicity, as shown in the figures below. So that's the figure over here. So now what's happening is the system starts at that little dot, this pink dot over here, or this pink dot over here, and it stays in this side of phase space. So it only samples the states which are all more or less pointing up, and it never goes into the other region where the states that would compete against those and give you a net magnetization of 0. None of those get entered, and so you can have a non-zero magnetization. So what the bottom line of that is that the Boltzmann distribution is not the correct distribution for describing statistical mechanics. It's true for T greater than Tc, but when you have phase transitions, when you have order, when you have emergent phenomena, then what happens is you actually have two probability distributions below Tc, either this one over here, where it is only in the positive part of the phase space, say over here, and then, or this one over here, where it's only in the negative part of phase space, say over here. And so you have a choice between those two things, and which one you have depends on what the initial condition is. And what I told you was that if you ask, the system starts off in some region of phase space, and now you let it wander, how do I know that you really get ergodicity breaking? And the answer is a formula, as I wrote for you down here, which says that the time it takes to go from one region of phase space to the other scales with the size of the system as e to the n to the power d minus 1 over d. So if d is 3, for example, that would be e to the n to the 2/3. As I take the limit n goes to infinity, that time diverges, and so the system gets trapped in a particular region of phase space. So what I want to do now is I want to start off by showing you how we can derive that formula. And in deriving that formula, what we are going to be doing is we're going to be thinking about phase transition kinetics. I'm not going to go into this in huge detail. It's an immensely interesting subject. Some of it is covered in the class on non-equilibrium statistical mechanics that we have in this department. I'm going to just give you a very simple elementary introduction to it and use it to explain the ergodicity time formula. And then in the second part of today's lecture, we're going to formally do mean field theory for the Ising model. Now, up to now, we talked about a 10-second theory for the Ising model, okay, and that's part of the homework. And that 10-second theory just used symmetry and analyticity. In the mean field theory, now we're going to start doing honest calculation. So this is more like this is more like a 5-minute theory rather than a 10-second theory. And later on in the class, when we talk about the normalization group, that's probably a 3-day theory rather than a 10-second theory. Okay, so let's get started. So what we're going to think about is the following situation. We're going to think of a system that is a magnet. So we're going to now derive the ergodicity time formula. And I'm going to kind of use this as a way to introduce you to a kind of universality. So I want to think, first of all, let's suppose that we start off with a lattice, and we have spins on this lattice. I'm not going to draw them all. I'm just going to put them in sort of metaphorically like that. And what we're going to consider is the following strategy. We're going to think that we start off with H to being non-zero and in the positive direction. So we start off with H like that. And then we're going to ask, so we're going to set that up. And then the question we're going to ask is, how does the system make a transition to m less than 0? So we're going to start off magnetizing the spins, and then we're going to ask what is the probability that we will go to make a change where m is less than 0. So in this first part of this calculation, m is going to be positive, and then what we're going to do is we're going to add a twist to this. We're now going to then imagine reversing the magnetic field. Imagine reversing the magnetic field. And making m less than 0 the stable state. And from that, we're going to ask is then how long it takes to do that, how long it takes for m to change sign. So that's the picture, and then think of it like this. I'm going to draw my system. So here's the picture. So now I'm going to have an external magnetic field. Why not make the external magnetic field point down? And I've got all the spins in the system have been magnetized to be pointing up. So that's the state of the system. And then this is what happens at t equals 0. And then the question I want to ask is, as time proceeds, so I get to some future time, what is going to happen is the system is going to end up like this. With all the spins pointing down, and I want to know, and in this particular case, this picture, then this is now an unstable state. And this is a stable final state. Okay, so let me just review why the initial state is unstable. The initial state is unstable because I first of all prepared the spins to be pointing up, but the magnetic field is pointing down. And when the magnetic field points in a certain direction, in the Ising model Hamiltonian, the spins minimize their energy by pointing in the same direction as the external field. So here, the spins are all pointing in the wrong direction. They're in the opposite direction to the field, and so that means you have a high energy state. And if it's a high energy state, then the system wants to lower the energy by going to a low energy state. So in the final state here, the spins point in the same direction as the field, and so that means it's low energy. So that's the cartoon picture intuition. All right. So now let's think about how we're going to do that, how we're going to understand this question. And so now I'm going to move the goalposts on you. So I'm now going to use your intuition in a different way. And this intuition in a different way is I'm going to introduce you to the idea of a lattice gas. Okay, so let me say what I mean by a lattice gas. So let's suppose that I say that when I have the spin being up, when that is +1, that is equivalent to there being a particle in the system, particle at that lattice point I. And if Si is -1, then there is no particle at that lattice point I. Okay, so that's that. So that says if I take a spin system and I draw the spins like this, so maybe here's the up spins, down, up, up, down, down, up, up, something like that. Then in this particle analogy, that would map into a configuration that looks like this. So wherever a spin is pointing up, I put a particle. So there's a particle over here, there's a particle over here, a particle over here, and then there's two particles over here. So that is a picture. And as these spins are flipping, as the movie is running, as it were, these particles are moving around on this lattice. So there's a mapping then between a spin system and particles. And you can think of this as being, this is like a gas that lives on a lattice. And in a sense, this is why it is the case that the magnetic phase transition and the liquid gas phase transition have the same behavior, that I can map from one to the other. And it's easy to think of this. All I have to do is say that the density is 1 plus Si divided by 2. So this is particle density, particle number, and this is spin. And so you could take the Ising model Hamiltonian, you could then plug this transformation in and get a Hamiltonian that describes how gas particles move around. And that is, you'll find also in my book, and you can look at that there if you are interested. Okay, so now we have this idea that there could be an analogy with a liquid gas transition. So now what I'm going to do is I'm going to say, let's answer this question about how the phase transition occurs by answering it in the liquid gas transition. So the next thing we're going to do is we're going to look at the liquid gas transition. And the reason I want to do it like this is because it's easier to think of particles bouncing around in a box than spins flipping. So let's think of a cartoon picture of what happens when I've got particles bouncing around in a box. So here's my particles, and they're in a gas, and this is above, let's say, the critical temperature. So you just have a gas. And now let's suppose I go below the critical temperature, and the thing would like to be in the liquid phase. So what is going to happen here? So I've still got my same particles bouncing around. So what are they actually going to be doing? So I want you to think about this as a cartoon. I've got my particles in the room bouncing around. The stable state is below Tc. So the stable state of the system is it wants to be in a liquid state, but it's only going to be in a liquid state when it gets to very long times. Okay, so you start off in the gas state. So what's going to happen is the particles bounce around, and then every now and then, 2 or 3 of them come together like this, and they form a little cluster of atoms. A little cluster of 3 atoms sits there, and then another atom comes along, hits it, and they bounce off and they fly away, and that cluster is gone. Okay, so now you wait a little bit of time, let's say 1 million years, and maybe then 5 particles come together here, and they sit there for a little while, they're sitting around like this, and then all of a sudden another particle comes along and one of them flies off, and bang, that little cluster of particles disappears. And then you wait another maybe a couple of billion years, and maybe you find now, let's say 50 particles, just by chance, all happen to get into the same area, and you make a little cluster of particles, 50 of them. that cluster is a big enough droplet that that it has the potential to expand, and then other particles run into it and they join the droplet, and gradually the droplet grows and eventually fills the system. So that's the process. There's many, many attempts for the gas particles to come together and form a liquid, but they form a little droplet that is too small and eventually evaporates. And only after a very long time do you actually get the phase transition. So let's have a look at how that happens mathematically. So what I want you to think about then is, here's my physical system. And the process that I just described in cartoons is a picture like this. Here in the middle is my cluster of particles that have all come together. I use the example of 50 of them or something like that. So let's pretend that there's 50 of them. This little droplet has a radius, which we will call r. And then out here, so here there are gas particles. I'll just draw them like that. And then in the middle of this thing, we have a liquid drop. And this might happen at, say, I don't know, t equals 300 million years. But 300 million years is still less than infinity, all right? So let's ask what is the behavior of this droplet. So to do that, I need to work out what its energy is. So remember here, I've said that the liquid phase is the stable one at this particular temperature. So let's have a look then at what the free energy of the system would look like. So I'm going to draw here the free energy as a function of the as a function of what chemists would call a quote reaction coordinate, which in this real case is something like the radius of the droplet. So here is the free energy. I'm going to draw another curve in a minute, which is something related to this, but not quite the same. So this is the free energy that you would have if you had an equilibrium free energy. So it would look something like this. This phase over here, actually this reaction coordinate is not R. I made a mistake in saying that. I'm going to take that out. I'm going to think of this as being something like density. All right, so let's suppose that I'm in this low density phase here. So this phase here, this describes the gas phase, which has got a higher energy than this other phase, which is here, which is the liquid phase. Okay, so the liquid phase is the one that lowers the free energy of the system at the temperature that we're talking about, this temperature less than Tc. And so the picture I just described for you, this cartoon picture, what it corresponds to in this picture is something like this. It's something like particles sitting in this well here, and then as they come together, they change the density a little bit. You have a local region where there's a few particles clustered together, so there's a higher density there. So they're exploring this curve, but they're just sort of oscillating around in the minimum there. So this process where you have two particles come together, then you wait a million years, then three particles come together, you wait a million years, two particles come together, you wait another 10 million years, five particles come together, you wait another million years, and so on and so forth. That is just the system oscillating around in this potential well. And when I said after you waited for 300 million years and you formed a droplet, what has happened is by chance the system got to here. And if the system made a density fluctuation this big, then you can see that what could happen is it could fall back in this direction, and then you'd just be back to a gas again, this process of evaporation, particles coming together and then flying off. But it could also go down this way, and as it goes down this way, more and more particles glom onto it, and this droplet grows until eventually you get to the liquid state. So what we have to try to understand is the question of how this gas, which is below Tc, so it's super cooled, how this gas gets enough energy to go over the free energy barrier separating gas and liquid. So that is our question. So let's draw some axes here. So here there is we can see that the liquid state is more stable than the gas state by an amount of energy. And I'm going to call that amount of energy epsilon. And then there's going to be a free energy barrier here, which I will call delta F. And that free energy barrier, if you can overcome that, then you will be able to go into the other state. So this delta F depends on the radius of our droplet. So let's compute how does delta F depend on the radius of the droplet. So delta F as a function of droplet size has two terms. First of all, if the droplet is in the liquid phase, as we've said the droplet is over here on the left, then it has lower energy by an amount epsilon per unit volume compared to the gas. So the volume of the droplet is 4/3 pi r cubed. So the free energy is minus 4/3 pi r cubed. That is the energy benefit from being in the liquid phase. Energy benefit being in the stable liquid phase. And this epsilon is per unit volume. Okay, so that's the first term. Now the other term is one that is a positive term, and that comes about because if I've got a droplet like I have over here, that droplet is a boundary between the gas and the liquid. And the boundary between a gas and a liquid, when I'm below Tc, has a certain amount of energy associated with it. You've seen the meniscus in your water cups over there, for example, in your coffee cup. So there's a meniscus that is the surface energy of the liquid-gas interface. So this has a surface energy density, surface tension, if you will, per unit area. And that we'll call sigma. And that is because it is the meniscus separating the liquid and gas phases. So then that means that over here on the right-hand side, 1 second, then I'm going to have a term that is proportional to the surface energy, and then the surface area is 4 pi r squared, and so I have a term like that. Yeah, what was it? What's the question?
When you're talking about like the meniscus, you're talking about like the molecules or the atoms, whatever, wanting to stay together, right?
Yes.
Like,
Yes. Yes, no problem. So inside here, all the liquid atoms like to be close to each other, and so that pulls them in here, and then you get the surface energy of this. And it costs a certain amount of energy to add another atom.
Yeah. Okay.
Yeah.
Thank you.
Yep. You have a question?
Maybe what do you want to do part of the sequences?
It's not the volume. It's per unit volume.
Oh,
The quantity epsilon is an energy benefit per unit volume of how much of that phase there is. Okay, does that answer your question? Yeah. All right. So if we take a look at this, so then this thing here is the this term is the cost of making an interface between the two phases which in this case is the gas and liquid phase. Okay, so that's where this comes from. So that's the free energy. Yes, go ahead.
Can you explain the minus
Can I explain you fine?
the minus one? Why is there no?
Oh, there's going to be an epsilon. Was that your question? Yeah, you're totally right. I was saying it and interrupted myself from writing. Thank you. Yeah, there's obviously an epsilon there. Right. So this is all just equilibrium free energy. Now we have to ask a question of what is the rate of going over this barrier. So now we have to use a result from non-equilibrium statistical mechanics, which can be derived. And that result says the following. The result says the following. The time for a reaction to occur is tau is proportional to E to the delta F over kBt. Okay, those of you who've done chemistry, well, I know most of you have, you'll intuitively understand this. This is the Arrhenius factor. It says if I have a reaction, if there's a very high energy barrier for it to happen, then the time it takes for it to happen is going to be long. And you say, well, it just goes as e to the delta F over KT. That's kind of like a Boltzmann factor, right? So everybody's sort of comfortable with that, okay? Except you should be very, very uncomfortable with this, because this is a total scam. This part of the calculation. First of all, this delta F is then a function of R, so that's the first thing. This then is called the sort of Arrhenius law. So this is the time for a reaction to occur. This is Arrhenius law. And the reason why it's a scam, and we're not going to resolve the scam here, it's a scam because we're talking about a non-equilibrium process. So then if it's non-equilibrium, where does temperature come in? There's no temperature if you're out of equilibrium. Temperature is an equilibrium concept. If I'm looking at a phase transition kinetics, I'm looking at how the system moves from one state to another. I'm looking at the non-equilibrium dynamics. How can I define the temperature? Okay, so it's a very subtle issue, and I'm not going to resolve it. So let's just use the ideas that, well, you still have some sort of background temperature, and you can think of that not changing very much, and so then you can look at the kinetics on this kind of background. So some kind of thing like that will sort of pull the wool over your eyes, and you'll say, okay, fine, let's just move on with it. So I'm not going to explain that. To do this properly, you have to do an honest calculation where you do the statistical mechanics, you look at the stochastic process, you look at the fact that you're near equilibrium, and then you compute the rate at which you go over an energy value using what's called a Fokker-Planck equation, and you can derive this, but it's not trivial. So think of this for now as being a sort of slow non-equilibrium process. And if that makes you feel comfortable, then we'll just go with that. So then what that means is if I draw my delta F, it looks like this. So when R is small, the term that's going to dominate is this term over here. So it's going to start going up like this. And then there's going to be a maximum. And then when R is large, this term over here is going to be the dominant term. And so then it's going to go down something like that. And so this process of going uphill is a slow process going up here. And then this here is some large fluctuation. And I'm going to call that the critical droplet. And then down here, now the system is going downhill, and so an energy fluctuation reduces the free energy, and this goes fast. So I'm going to understand how long this transition occurs, then all I really need to do in order to calculate the time of the transition I just focus on the slow uphill process. So in other words, we focus on the question, how long does it take to get to the critical droplet? And that critical droplet will have a size, which I'm going to call RC, and that size is the stationary point of the free energy. So that is equal to 0 when R is equal to R star. So I just have to differentiate that. Even a tenured professor can do that calculation. And when you differentiate that, so what you get is you said that that thing equals to 0. So that should then be 8 pi sigma R star equals 4 pi epsilon R star squared. And so that then tells you that R star is 2 sigma over epsilon. And so therefore, if I compute the free energy at the critical droplet, delta F of R star is equal to 16 over 3 pi sigma cubed over epsilon squared. Okay, so that is the free energy value for that critical droplet, and the time it's going to take to get there is going to be proportional to e to that number. Okay, so the time is going to be proportional to e to the delta f of r star. That is the time. Okay, so that's the liquid gas transition. Now let's go back to the thing that we actually wanted to calculate, which is the ergodicity time. Okay, so the next thing we're going to do is now use this to calculate the ergodicity time. So what is the idea for that? So let's just go back and look at our states here. So this state over here, this gas state, that is the state that we call a metastable state. It's a local minimum, but it's not the global minimum. So this state here is the stable state, and it's the stable state because this state is equal to the global minimum. And this one over here is a local minimum. Okay, so we have that picture of our local minimum. So let's now let's go back to our magnetic example, and let's ask in the magnetic example. So we have an external magnetic field that I have pointing down. And then my metastable state is all the spins pointing up, and my stable state is all the spins pointing down. So that is the picture, and the the energy gain of being in the stable state, that gain is epsilon, and that epsilon is proportional to the strength of the external magnetic field. So normally the spins being up, the spins being down, they're the same energy. The energy is degenerate. But if I have an external magnetic field, then that biases the energy. And so the amount of bias of the energy is then proportional to H. So the question that we want to understand then is, for ergodicity breaking, we actually want H going to 0, and H is going to 0 from below. And so what's going to happen is, if you look at this formula over here, this is where epsilon is. It's in the denominator there. So then what's going to happen is the epsilon is in the denominator here. So as H goes to 0, what that means is R star is going to infinity. So they take the limit, those states become more or less equal value, and the critical radius of the droplet is going to infinity. Now it can't go to infinity. Okay, can't go to infinity. So let's just see why not. So, but R cannot go to infinity. And why can it not go to infinity? It can't go to infinity because we've got a finite number of atoms. We've got a finite size box. So it can't go to infinity because the number of spins, or number of atoms, is equal to n, and n is a number that is less than infinity. So what's going to happen then is that when I think of my finite size box, so here's my finite size box. Looking something like that. And inside here, I've got n spins. So the size of this box is going to be L. L is proportional to n to the 1 over d. Why? Because I've got d dimensions. And so L to the power d is proportional to the number of spins in the box. The box has linear dimensions of L, then L to the d is equal to n, so therefore L is proportional to n to the 1 over d. So what that means is that as I set H goes to 0, from below, R star goes up, and then eventually must saturate at R star, the radius, is a number that is some constant, doesn't matter what it is, times L, and therefore is a number times n to the 1 over d. So now if I look at the free energy difference, so delta F, as epsilon goes to 0, which means as H goes to 0, that is going to be 4 pi sigma sigma cubed over epsilon. So that's n. Well, what I want to say here. Let me write it like this. Yeah, this delta F then, plugging into this formula, putting this into here, is then 4 pi sigma times n to the 2/3, or in d dimensions, it would be some number times the surface energy times n to the power d minus 1 over d. So what I did here was I computed what R is, plugged that into this formula for delta F, and then computed that in terms of the radius. And so because the radius goes as n to the 1 over d, then delta F goes as n to the 2/3, and therefore, and in d dimensions, so this would be true in d equals 3, and in d dimensions, arbitrary d, it'll go like that. And so then, now I plug into the Arrhenius formula, and that gives me that the time is going as some microscopic time times e to the power n to the d minus 1 over d with some coefficient here of order 1. And why is this what we wanted? This is exactly what we wanted, because now it tells us that as n goes to infinity, tau ergodicity goes to infinity. Okay, any questions? Yep.
Maybe I point, but you started off with example of droplets,
Yes.
and then you sort of find the parameter droplet R. How do you tie that in the magnetic case scheme?
Okay, so the question is, how does the liquid droplet picture apply to the magnetic case? So good question. So let's go over that again. So here is the picture in the droplet case. Here is the picture in the magnetic case. So I'm drawing it on the left-hand side. So here, now what I've got is I've got a stable state where H is in the negative direction. So inside the droplet, the spins are all pointing down. Those are the stable ones. And then outside the droplet, the spins are all pointing up. So the spins pointing up are the metastable phase, and the spins pointing down are the stable phase. And there is a surface tension, because when I have a spin pointing up and a spin pointing down next to it, the energy is e to the minus j if you look at this Sij term, this is bigger when one spin is pointing up and one spin is pointing down, because there's a minus for this one, and a plus for this one, so that cancels out this. And so when I have spins next to each other, which are in different orientations, there's an extra energy associated with that, and that is like the meniscus of the liquid drop, the energy between the gas phase and the liquid phase. Okay, does that answer your question?
So
What part didn't I answer?
I'll have to move that stew.
Let it stew for a bit, okay? Well, we'll let it stew, and then come back and ask me. Any other questions about this? So I've rushed through it. It's not a detailed mathematical theory. It's the skeleton of the theory, but I think you can understand the basic principle of where that calculation comes from. So, what the coefficients are, whether they're 4 pi's or 4 pi's over the gamma function of 79 or something like that, I didn't answer that. But in terms of understanding how the ergodicity time, when H goes to 0, so the states become degenerate, that ergodicity time then scales as the system, number of particles in the system, and it scales as e to the n to the d minus 1 over d.
So in liquid gas transition, the state at the top is R becoming some saturated value. So how would that look like in the spin transition?
So in the liquid gas transition, so I'm at a point in the phase diagram where the liquid phase has got a lower energy than the gas phase. Okay, and so there's a finite size for that droplet, and I mean that's literally what happened in an experiment. It rains, right? So the same thing would happen in the magnetic system. Now, the question we were asking in the magnetic system is not the one we were asking for the liquid gas system. In the magnetic system, we were asking what happens when H is equal to 0, and I put the system into a state where it's, say, got a positive magnetization, and I ask, how long does it take to get to a state with negative magnetization, when there is no external magnetic field? So what I did was I worked out what happened when there is an external magnetic field. I used nucleation theory for that, and then once I got that result, then I sent H to 0, and I noticed that the radius of the droplet will eventually cannot grow bigger than the size of the system, and the size of the system scales into the 1 over d.
I just wanted to know how the system looks at the top, where there's the convexity becomes. You have an upward.
Right. So you're asking. So you're asking what it looks like here,
Yes.
and what,
The spin system.
and it looks like this. Okay. I've got an external magnetic field pointing down. The spins that happen to be pointing down, like the ones in the middle, those have got a lower energy than the spins outside, which are pointing up. And as I make the external field go to 0, the difference between the spin pointing down and the spin pointing up state goes to 0. Just like in the liquid gas transition, if I go towards the phase transition boundary, the two things have the same energy, and then the radius of the critical droplet grows to infinity, but it can't go to infinity because it's got to stay inside the box. So we're doing a calculation of the system being finite. We do the calculation, and then we ask what happens as the system becomes infinite. And what we find is that the time for it to make that transition diverges. And that, because that time is divergent, that means the system is trapped in one part of phase space, and that's ergodistic working. Okay, one more question, then I'm going to move on.
When you were looking over some of the math, time, your ergodicity time, your spiel about the finite dimension, the finite size of R, I'm guessing that was to make an argument that there is always a finite time.
No, do you mean do you mean this argument here on the left hand side?
I mean, if R was infinite, I mean the change in free energy is equal to proportional to the cube of the radius. So if the radius was infinite, that would make delta F negative.
Right. R can't go to infinity.
Right, but that's what I'm saying. So you're trying to make an argument that there is always a finite ergodicity time.
There is always for a system with a finite n, the ergodicity time is finite.
It can't.
But
just that.
That is possible, but very unlikely. That would be as likely as all the gas molecules in this room suddenly going into that corner over there, and then we all end up lying on the floor gasping like fish that have just been caught out of a river. So that could happen, but I've never seen it happen in my life, and neither of you and neither has any other person. Okay, so the phase transition could occur instantly, but in practice, it's the mean first passage time is what's going to happen. Okay, I'm going to move on, and we're going to talk about the next topic now. And the next topic is I want to do a simple, honest calculation of mean field theory for the Ising model. Okay, so what is our goal here? Our goal is we want to compute the critical behavior of the Ising model. We want to do it in the mean field theory approximation. I'm going to say what mean field theory really means. And what we're going to end up being able to calculate is we're going to compute the critical exponents. I'm going to show you that we can compute scaling functions. and all the phenomena that you see in the real phase transition. And you might ask, why are we going to do this? Why not just do the normalization group? And the answer, the practical answer is, with very little effort, we can recapitulate virtually everything you see in experiment. So if you're a theorist, how many people here are going to be theorists when they grow up? Okay. How many people are going to be experimentalists? Okay. How many people are going to be working on Wall Street? Okay. If you're going to, so whether you're an experimentalist or a theorist, or even working on Wall Street, the first theory you should do is always mean field theory. You should always do this type of theory because you'll get 99% of the answer with 1% of the work. Okay, and the fact that it can't explain everything is, of course, why we have to go and dig deeper and further. So let's go ahead and let me show you one way to do mean field theory. There's a million ways to do mean field theory. I can show you how to do mean field theory using functional integration and all sorts of things like this. I'm going to show it to you not like that. I'm going to show you the very, very simplest theory. In probably the next homework set, I'll give you a chance to think about mean field theory from the point of view of functional integration. Of course, I'm using this fancy language, but when you see the homework set, you'll just see that it's some big multiple integration. Okay, so let's talk about what the problem is. So here's our Hamiltonian. So H is equal to minus J sum over ij si sj minus H sum over I si, like that. And these sums go from 1 to n, and so on. And the spins are plus or minus 1. And then I want to compute the partition function. And the partition function is the trace of e to the minus beta h, which means I take the product over all the spins. So I've written this down for you before, so I'm just going to write it in this shorthand like this, e to the minus beta h. And this is equal to, I'll just write it down because I'm nice. Okay. So that's the problem that we have to solve. So the first question you should ask yourself is, well, why is this so hard? Why is it hard? Why is it that you're only learning now in graduate school how to do problems like this? Why didn't you learn this on your mother's knee? Okay. Okay. Are there magnetic systems that you do know how to solve exactly, which you did learn on your mother's knee? Huh? No, not this in 1D. You didn't learn that on your mother's knee. The two-state power magnet. Thank you. Okay. So why is this hard? Okay. So the answer to that is, why is I'll use exactly your language, the two-state power magnet easy? Okay, the two-state power magnet is the following. This thing here is a ferromagnet. This is the full Hamiltonian. Okay. So the paramagnet is where there's no interactions. So we throw this term away. So then you just have this term. Okay, that's what we mean by the two-state paramagnet. So why is the two-state paramagnet easy? So you learned how to solve that. I'm going to show you again how to solve it in just 5 minutes. Okay, but why is it easy? And the answer to that question is what? Somebody is not you. Even though I am sure you know the answer. Wait. So let's just remind you what a paramagnet is. Paramagnet is non-interacting spins.
The exponentials are.
Thank you. So they're non-interacting. So that means that J is equal to 0. There's no interaction. There's no exchange interaction. So the paramagnet is the spin equivalent of the ideal gas. The ideal gas, there are no interactions. The particles just bounce around in the box. In the ideal paramagnet, the spins just flip independently and they don't care about all the other spins in the system, but they do care about the external field. Okay, so in this two-state paramagnet, why it is easy is that the partition function factorizes. And so virtually all the tricks in statistical mechanics, all the tricks in many body physics, all the tricks in quantum field theory, all of the tricks to be able to solve things are dirty tricks that enable you to figure out some weird way, some weird coordinate system where the partition function factorizes. That's what everybody's obsessed about. That is the thing that enables you to solve problems. If you can't do that, you're stuck. Okay, so factorizing the partition function is the thing that makes life easy. So what is our strategy going to be? So what we're going to do in this section is we're going to do the following. We're going to try to find an effective spin model that can be factorized and also has J not equal to 0. And the way we're going to do that is we're going to represent the spin interaction as the interaction with a carefully chosen external field that mimics quantitatively the spin-spin interaction. And if we can do that, if we can make it into such a system where you have this, you represent the spin-spin interaction as the interaction with the carefully chosen external field, then you can solve that exactly. So that's the trick. So let's see if we can make that work. Okay, so step one. We're going to set J is equal to 0. So now we have a paramagnet. And the Hamiltonian then is just minus h times the sum over I equals 1 to n Si. And so therefore the partition function, which is a function of 0 and h, so this is where J is supposed to be, so J is equal to 0. So what is that? That is the sum over all the spins equal plus or minus 1 of now e to the minus beta h. So it's beta times h times the sum from I equals 1 to n Si. That's what the partition function is. And this term over here, because this is the product, this is the e to the sum of something, that means that e to the x plus y is equal to e to the x times e to the y, right? So therefore this thing So therefore this thing is a factorizing product. This term over here. And then this term over here, the actual trace, this thing also factorizes. Why does it factorize? Well, it's just this. It's just that. That's what it means. That's the shorthand. So it factorizes explicitly. It explicitly factorizes. So therefore, I can write my partition function as z of 0 and h is equal to the product from I equals 1 to n, and then in here, the sum of Si is plus or minus 1, and then here, e to the beta h sum, there's no sum, e to the beta h Si. Okay, so that's what it factorizes to, the product of all of those terms. Notice that I, the label I, is this label here, and this is a dummy variable. Okay, I'm just going to factorize over that. It doesn't really matter what it is. So here's the I over here. Inside each of these square brackets, inside this square bracket, let's just write it out in full. This says, first of all, I have S is plus 1, so I have e to the beta h. And then S is minus 1, so I have e to the minus beta h. So that's what that square bracket equals. And then I do the product from I equals 1 to n. So this then is just, the whole thing is then just e to the beta h plus e to the minus beta h raised to the nth power, which is 2 cosh beta h, all raised to the nth power. So that's the partition function of the power magnet. Okay, it took 2 seconds. Okay, so now we've got that, so what? Well, remember that the free energy is minus kBt log z, and the magnetization is 1 over n, the sum over I, Si, which is minus 1 over n df by dh. And we derived that before, so I'm not going to go through that. So now all I've got to do is take the logarithm of this 2 cosh beta n, that gives me the free energy, and then differentiate it. So if I now then do this calculation, what I get is kBt over n, and then d by dh of the logarithm of z of 0 and h, and then that is then equal to, so log of 0, so log of z of 0 is 2 cosh beta h. So the derivative with respect to h of cosh is 1 over cosh times shine, which is tanth. So this then is then equal to tanth of h over kBt. And what happened to the factor of n? Well, this factor of n down here cancelled with this factor of n over here on the left when I took the logarithm. And then the kBt, where did that go? So the kBt, that kBt cancelled with when I differentiate with respect to h, I have a factor of kBt in beta. Beta is 1 over kBt, and so that cancelled as well. And so that's the final result. So that's the magnetization for a power magnet. Okay, so now let's do step 2 of our argument. So step 2 is we're now going to switch on we're going to switch on J, and the way I'm going to write this down is the following. So we're going to switch on on J. The J coupling between the spins, this thing over here, means that the spin over here now feels 2 things. It feels the external magnetic field, but it also feels the J from the spin next to it, either be plus or minus. So that what that means is that each spin fields, the effect of its neighbors plus the effect of an external field. So that's our intuition. So let's see how that works out. So the way I'm going to do this calculation is I'm going to write the Hamiltonian of the system, my Ising Hamiltonian, so the same Hamiltonian, I'm going to write it as an effective paramagnetic theory. So the paramagnetic theory was like this. I had I equals 1 to n of SI times an external field, H, but now we're going to allow that external field to depend on the lattice site I. And why does it depend on the lattice site I? Because it's looking at its neighbors. And because it's looking at its neighbors, the neighbors of lattice site I are the things that are going to exert the force on it. So I'm going to ask, what HI could I write down that would be exactly identical to the Ising model Hamiltonian? And if you think about it, what that is this HI, the external field, is just equal to the external magnetic field plus the sum over the neighbors of the site I. So let's call those variables J, the neighbors of site J, and then the capital J, and then the spins that are the neighbors. So this is exact. And if I then plug that into the Hamiltonian, then I can say that I can write that, well, first of all, this is exact. So and moreover, I can write down this HI is equal to H plus I can write it down in this way, sum over J, J I J S J, where J I J is equal to J if I and J are neighbors and 0 otherwise. Okay, so now what I'm going to do is I'm going to take that term and I'm going to plug it in to the Hamiltonian. So our Hamiltonian now looks like this. It's H plus, and I'm going to write it in this weird way. Let me write it in this weird way, and then I will explain to you why I wrote it this way. Okay, so let's just do a check. So here's something strange. This term over here, this really means the mean value of the spin at site J. This is the mean value of the spin at site J. And one of them is positive and one of them is negative. So they actually cancel out. So if you throw that term away, then what I have left is the original Ising model Hamiltonian. Actually, let me, I've said this is the H, but it's not. It's the external magnetic field. I'm sorry. Okay, so I've written it down like that. So why do I write it like this? This term over here, well, actually, this term, this term over here is the fluctuation about the average value, the mean value of the spin Sj. So I take the instantaneous value, I take a snapshot of the system, it has the value Sj, its deviation from the average is Sj minus Sj. So I call that then the fluctuation about it. So this is the fluctuation about the average. This term over here is the mean value of the of the contribution to this field at site I. It's the mean value because it comes from the mean value of site Sj. And where I'm going with this is that when I ask what is the mean value of Sj, the answer is that is the magnetization. That's the thing that we know, and that is independent of the site I or the site J. So what is the mean field approximation? The mean field approximation is that we're just going to take these first two terms here and we're going to ignore the fluctuation. And why do we do that? Because that means that now HI is independent of I. And we can compute what it is. So if each atom, each spin, has little z neighbors, and on a hypercubic lattice, in d dimensions, little z is equal to 2 times d. So therefore, then what this HI is, this is some sort of effective external field, and this is going to be H plus this term over here, this mean value is 2d times j times m. And so what I've just derived is that the Hamiltonian for the interacting system is equal to the Hamiltonian of the paramagnet if you take the external field and replace it to H plus 2d times j times m. And if that's the case, which I've shown you it is in this approximation, then I can go straight back to this formula over here, where we already calculated the magnetization of the paramagnet, and so now we know that m is equal to the hyperbolic tangent of h plus 2djm over kbt. And this is an equation that eats itself, because I've got m over here, and I've got m over here. So it's a transcendental equation. Okay, so that's where we're going to end. So next time, we're going to solve this equation, and we're going to see that it predicts a phase transition. And all the things that we set out to do. Okay, so I'm going to leave it there. So any remaining, let me turn off the Zoom. Any questions?
So the interaction seem to be resulting in a phase movement.